Howdy everyone, I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I record all of my lectures and put them on YouTube so anyone can follow along and see what we're talking about. So I teach on data analytics, geostatistics, and machine learning, and this is a lecture within my data analytics and geostatistics undergraduate level course. Lecture 1 on statistics, and this is the data analytics. So let's go ahead and get started with some terminology. Now, first of all, statistics, been around for a while now. It's all about collecting, organizing, and interpreting data, as well as drawing conclusions from that data, specifically with the purpose to support decision making, making decisions. Now, something I tell my undergraduate students is if you do statistics and you don't impact the decision, you're in fact not adding value at that point. Okay, now geostatistics is a branch of applied statistics. It accounts for the spatial, if it's geology, if it's atmospheric, whatever it might be, the context, the spatial context, the spatial relationships. We'll talk later on about things such as variogram models for quantifying spatial correlation, volumetric support scale of the data, the models, everything. And we work across many different scales, and the uncertainty in everywhere. In fact, uncertainty in everything. In fact, I would suggest we even have uncertainty in the uncertainty. Okay, more on that later. Data analytics is, if you look it up, it's the use of statistics. That's kind of it. Maybe a focus on visualization, but always to support decision making, business data analytics, supporting managers making big choices. The thing that's very interesting to me is when I look at data analytics and statistics, I fail to find a significant difference. So I do feel that to some degree that there may be some rebranding going on here. If you know statistics well and you can use it to support your work and decision making, update your CV. You work in data analytics. Big data analytics is the process of examining large and varied data sets, big data, to discover patterns and make decisions. And so we could go ahead and draw a Venn diagram. We'll get into Venn diagrams next section, but this idea of how concepts overlap and interact with each other. Statistics would be a very large area of study. So many things we can do. And geostatistics is that focused area with the applied branch that I mentioned. Then we have big data, where we have big data overlapping with statistics. We call it big data analytics. And where it overlaps with geostatistics, we could call it spatial big data analytics. I think that's fair. Now let's go ahead and talk about, as we're doing data analytics and statistics, let's go ahead and talk about what are we working with. Our fundamental building block is going to be a set of variables. Now, in data analytics and machine learning, we like to call them features. Same thing. Any property of measure observed in a study over space or time or whatever the domain of the study is. In the subsurface, it could be porosity, mineralogy, saturations, water, oil, gas, mineral concentrations, contaminant concentration if you're in an environmental soil study. In data mining and machine learning, we're going to use the term feature, and we'll talk about predictor feature, response features, and so forth. Now, the measure often requires significant analysis interpretation. And so when we say something's a feature, we have to step back and admit that there probably was work that went into actually making that calculation. Many of the features we work with, we don't directly observe. We have to do some type of analysis to back out some type of inversion, some types of interpretations in order to get to the feature. And we'll talk more about that hard and soft data. Now, we deal with populations and samples. The population is defined as the exhaustive finite list of the property of interest over the entire area of interest at sufficient resolution to solve your problem. In other words, the entire population would be the entire thing that you want to study with sufficient resolution that you can actually make your choices. Now, too bad that typically is not available to us. We generally don't have access to the entire population. Now, the sample is going to be the set of values with their locations, the specific features that have been measured and observed. For instance, in this case, we have some type of a reservoir with pore volume. We have multiple fluids filling it up, water, oil, and gas. And this would be the entire population. Then we have a single well that's drilled through here. We've taken some information along that well bore. And so that right there would be the sample that's available to us. Now, I'll say it right now, and I'm going to say it over and over again in this course. We typically sample only about 1/trillionth volumetrically of the reservoir directly. Okay, so expect the sample to be very different from the population. Now, when we're talking about population sample and we're talking about the information from them, we're now talking about parameters and statistics. A parameter is a summary measure of the population. Okay, so a population mean, the arithmetic average over this entire finite set of values at sufficient resolution, population standard deviation, and so forth. We rarely have access to these population measures. What we have access to are statistics. Now, you'll see when we get into hypothesis testing, confidence intervals, we'll use tools to get at uncertainty models with regard to the population parameters, even though we don't have access to them. Statistics. It's a summary measure from the sample itself. So I've extracted a set of information along the well bore, 1/trillionth of the reservoir sampled directly. And now we're going to have a summary measure from that. Sample mean, sample standard deviation. We're going to use statistics to estimate the parameters. And let's get into that. Let's talk about that. Further breaking down the features. Okay, so we have predictor and response features. When we get into machine learning or when we're trying to build a predictive model, it will often take on a form like this. We have a system with predictor features. Those are like the input variables, input features, x1 through xm. Now, we'll also have the y, and there might be more than one y's. They're the outputs. They're the things that we're trying to predict. That's the response feature, or it could also be known as dependent variables. Same thing. It's the output. It's the y's. Now, data analytics and machine learning is all about building these types of models for really two purposes. I already stated prediction, but we could also be doing it for inference. So inference and prediction are the two modes of operation. Now, let's talk about inference first. Inferential statistics is given a random sample from a population, describe the population. That's the inferential workflow. Given the well samples, limited, remember 1/trillionth of the reservoir sampled directly, tell me what the reservoir is going to be like, the entire subsurface, the entire population. I got a well, I got a sample, now describe the population. That's inference. Prediction is different. Prediction is you predict the samples given an assumption about the population. So we already had information, we drilled wells, we figured out a model of the reservoir or the population. Now for the very next location we're going to drill, give me a pre-drill prediction of what we expect to happen. And that would be a prediction problem. Okay, so inference, sample to the population, prediction, population to the next sample. Now when we build these types of models, that F that we're estimating to go from the X's to the Y's, we have a variety of different models we can build. We can work with and often do deterministic models. Those are an engineering geoscience type model where we assume we know something about the system or processes, and we're able to then make a prediction of what we expect to happen at the next sample location, or we're able to model the population and understand how everything, all the features interact with each other. That's relying on engineering physics and geologic interpretation and understanding of geologic processes. The statistical model approach is different. We say the system or process responsible for the system is uncertain. And now we're going to rely on multiple models constrained by summaries like statistics from the samples in order to describe the system. We have multiple models. So let's give ourselves a couple of examples. We have a data set like this, and this axis right here could be time, it could be space. Now, a deterministic model could be, I know that this is topography. and we're not in the mountains. We expect kind of a gentle, hilly type of topography. And so we could fit some very smooth type line through and say, okay, that's a reasonable model, what's going on in between the sample locations. That's a deterministic prediction model. Now, we could also say that, no, this is time, and this is the period of 1 day, 1 day, 1 day, and it's daily interest rate. And the daily interest rate doesn't change during the day. And so this would be a perfectly good deterministic model to use. A statistical model would be, let's describe the variance, the mean, perhaps a measure of spatial correlation like the semivarogram, and let's build multiple models that have the same statistical descriptions, but we don't know, it's uncertain, so we'll need multiple models, and we can now summarize at different locations based on those models. These are totally different ways to model a phenomenon, and the good news is you don't really have to choose between them, because I would say 90-something% of models I worked on in the subsurface and otherwise have been a combination of deterministic and statistical models, both put together. In fact, what you'll find is that a certain proportion of the variance is described deterministically and a certain proportion of the variance is described statistically, and the model put together is actually quite powerful using the best of both worlds. Now let's make a couple of more comments about this idea of a deterministic model. And so a deterministic model like this one right here, Kwanza Basin, West Africa, it's a stratigraphic model based on the seismic information. It was based on great expert knowledge about this type of basin, the diapirism, the way that in large-scale tectonics and loading and compaction and deposition and so forth all interact, accommodation and filling of sediments, a knowledge of all of that put together to build these beautiful, beautiful models. The advantage is you're going to integrate all kinds of available physics and expert knowledge, and you'll integrate various sources of information. This is a deterministic model. Now, what are the disadvantages? They tend to be quite time consuming. You could spend a lot of time building these models, and often none or very limited assessment of uncertainty. It takes so long to build one model, it's hard to imagine building a suite of models to represent uncertainty. You're focused on building one model. Now let's talk about the advantages of a statistical model. Well, here's an example of statistical model. It's a geostatistical realization with non-stationary or change in the local means. You can see that the porosity is high here on the crest. It's a carbonaceous setting. And as you move down the slope here, you get into finer grained type of breccia and sediments that have lower porosities. And when you get back here, you have lower energy. You got lower porosities again. So this is a model that has really nice heterogeneities in it, but we can build it very quickly. We can build realization number 1, realization number 2 of porosity, build many realizations. If you look carefully, you'll see lots of differences. You see the high porosity here, lower porosity. There's even a streak of low porosity right there, a streak of low porosity there. It's high on this one, away from the wells. We can have uncertainty assessment through the ensemble of possible scenarios and realizations, the different models. We'll talk more about that. We can report significance, confidence, prediction intervals. We can really build a nice uncertainty model. We can honor many types of data very, very nicely, and it's data-driven. It's very quick to do. Some may even say data-driven is more objective. I'm not totally comfortable with that because I think the subjectivity of interpretation has a lot of value too. Okay. Disadvantages, limited physics used. It's a statistical model based on the data. It's not directly accounting for the physics. Now, I did state that there was a trend model and I did tie it to some depositional processes, but at the same time, that was a deterministic component put into the model through mapping. So that was not the statistical model doing it. The statistical model actually assumed stationarity, didn't account for that. There's a lot of statistical model assumptions or simplifications, abstractions, which make the model quite portable and parametrically simple, but at the same time may reduce the realism of the model. So when we talk about stochastic modeling, we're really talking about statistical simulation models that we can build and get the right heterogeneity, which compels me to make a couple of comments around estimation versus simulation because they're both statistical models. Estimation is all about the process of obtaining a single best estimated value of the reservoir property, the reservoir feature, the spatial feature, at an unsampled location. Estimation is going to each location away from the data. Data are the black dots here, and finding the very best estimate at each location. Local accuracy takes up precedence over global spatial variability. And so these models tend to be too smooth. They're not appropriate for forecasting because many forecast models, physics-based models like flow, or maybe compaction, or maybe contaminant transport, or whatever it might be, they are sensitive to heterogeneity. We need to have realistic heterogeneities, and this is too smooth. Simulation, shown over here with the same data, is the process of obtaining one or more good values at a reservoir feature at an unsampled location. Here we had the best value. Here we have good values, possible values, not the most likely estimate. Now, global accuracy and matching the global statistics is the most important thing now, because then we'll say, okay, now we will get realistic forecasts with this model because it honors the global statistics. But since we've only have good estimates at each location, not the best ones, we now have to work with multiple models to represent the full space of uncertainty away from the data locations. Why would we prefer to work with a simulation model? Well, we need to capture the full distribution of properties. We know when we get into heterogeneity measures, we'll talk about Dijkstra-Parsons, which is really just a measure of dispersion of the permeability. If we underestimate the dispersion or variance of permeability, we're not going to get the flow right. Dijkstra-Parsons is a pretty good proxy to get some understanding about flow behavior. And so we really do need the full distribution. We need these types of models that have the full range of possible outcomes, not these that are too smooth, way too smooth. So we need realistic models for flow. Now, I should comment on the fact that mining and some other subsurface modeling areas actually do use estimation models more frequently than, say, oil and gas. And it's because they're less concerned about heterogeneity to some degree, because number one, they have more data available to them, so they can actually get the heterogeneity directly from the data. Denser space data in mining often, and their transfer function, and I'll get into this right away, is the calculation they use on the model to get to dollars or response or forecast is much simpler than flow simulation. It's more a volumetric averaging of concentrations or grades within the rock. So how do we do uncertainty modeling? Let's formalize this. What we'll do is we'll need multiple statistical simulated models. That's the best way to do it. And what we'll do is we can have a decision tree here of sorts. We'll say we have a reservoir. We have different conceptual models. Things can change dramatically. Maybe there's fluvial, maybe this is some type of deltaic, maybe this is deep water, maybe this meandering fluvial, this is more avulsing, and so forth. And then maybe we have model parameters that change. Maybe the fraction of sand may change, or the average porosity, and so forth. This is scenario-based uncertainty. We're going to have multiple models that have different modeling choices. So now we have 8 models that have different choices in them, scenarios. Now, if you keep the choices all the same, but you just change the random number seed so that you get a different spatial model under the same data constraints and choices, then those are known as, that's geostatistical uncertainty, a spatial uncertainty. And we will call these realizations, 1 through L. These right here were scenarios, and for each scenario we'll have multiple realizations, and that's the general methodology to build an uncertainty model using geostatistics. Now, the general workflow, if we're going to go ahead and build these uncertainty models, what we're going to do is we're going to integrate all available information into multiple scenarios and realizations, and we'll say that that has described the uncertainty, the multiple models. Then we can apply the models to a transfer function that gets us to a decision criteria. Now, this decision criteria or criterion could also It could include multiple, but it's going to provide you with something closer to, say, dollars. Recovery factor is a good one. It's the fraction of the connected pore volume in place that you can actually recover with your mechanism, drilling, enhanced oil recovery, and so forth. That's great because now you can forecast production rates for every one of the wells that you put in, given you know something about the connected volume for each one of those well trajectories. Then what we can do with this uncertainty distribution is we can now make the best choice, optimum decision accounting for this uncertainty. We can get into that later. I actually have a lecture in subsurface modeling, which is all about decision making in the presence of uncertainty, if you want to check that out. Now, what is the transfer function? Let's just go ahead and define that more formally. It's the calculation applied to the model. Deterministic, statistical model, it doesn't matter. We're going to apply this transfer function to hopefully all of the models. And so it's what gets us to a decision criterion. It might include things like volumetric calculation of resource in place. It could be the heterogeneity metric for estimation of recovery factor. It could be some type of flow proxy, a surrogate model that's very fast to run. Or it could be full flow simulation, multi-phase, accounting for all of the physics, and it could be much more costly and expensive to work with. Now let's finish up our discussion here with this introduction around statistics, and let's talk about the broad use of statistics. I'm a big fan of Hadley Wickham. Hadley is chief scientist at RStudio. And he's well known for the development of open source statistical packages for R to make statistics accessible and fun. I'm a big fan of R. I do a lot in Python too, but R has great documentation, very robust code, a lot of great programs and statistics that give you all of the needed outputs all at one time, the visualizations and so forth. Very nice for doing statistics. So Hadley Wickham had written a paper called Teaching Safe Stats and Not Statistical Abstinence. And it's a little tongue-in-cheek, but it's a really thoughtful thing. It's very short. I recommend it. Here's the link right here. I recommend everyone have a read of that paper. And what is his message from this paper? What's Hadley telling us? He says, if you're teaching statistics, you really need to rethink your statistics curriculum because we really risk becoming irrelevant, obsolete. And what's the problem? Well, currently statistics tends to be taught as avoid unless you are a statistician or work directly with one, have a PhD in stats. And the problem, what they say is otherwise you're going to cause great harm. It's scary. Statistics is very scary. But there's really not enough professional statisticians to go around. I remember when I was working in industry, I ended up doing work on repetitive stress injuries in our workforce because when we looked out across our research company, there was only a couple of us with PhDs in anything related to statistics. And I happen to have a PhD in geostatistics and data analytics. And so what Hadley said is rather than stigmatize the amateur and say, nope, don't do this, dangerous, scary, tools should be safer for use. And we should be teaching practical workflows, user-friendly tools for wider use of best practice and robust statistics. We all have a role to play in making statistics safe for the workplace and in academia. All right, thanks a lot, Hadley. I hope that this lecture was useful to you. It was a general introduction of some basic data analytics, biased towards spatial and subsurface, and some ideas around geostatistics, statistics, and so forth. The next lecture we'll get into sampling, the subsurface, and then we'll go ahead and we'll talk about issues around bias in the sampling. We'll do a lot more with that later on. And then we'll get into the different data types we have in the subsurface. Anyway, I hope that this short lecture was useful to you. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin. I post everything online and hope that it helps working professionals. If you want to work together, I have a research team that does a lot of great stuff and a consortium on data analytics, geostatistics, and machine learning. I'm more than happy to discuss. I'm easy to get a hold of. All right. I hope this was useful to you. Take care.